Recordings rolling. It is a new week, Monday, February 2nd. So I have a demo for you guys here at the beginning of class. Do some review. You guys remember last week we were doing harmonic motion. You guys had pendulums going and mouses on springs bouncing up and down. Okay? And so I'll do a quick review with you guys on that. All the blue paper overs, AP details, so don't worry about that. Okay, we're going to do a Kahoot later in class today. I'm probably on waves here. So the review I give you guys for the next few minutes will be probably applicable to a lot of these questions. Well, I also want to cover Doppler effect with you guys. There's a Doppler question here, and we'll want to do that anyway. All right, so I got the next week paced out. I think I'll get you guys your next in-class quiz on Monday. So 1 week from now, Monday. Okay. All right, so let's do an auditory demo from last week. Do a recap. All right, listen close here. All right. So were you guys hearing 1 beat per second? Is that what you guys were hearing? Okay. So make a table here. A table. Okay. All right. So you guys heard 1 beat per second. If I say the number of beats per second, right? Well, I think you guys were hearing one, right? 1 beat per second, right? That's a little bit different question though. Is what was the time between beats?
1 second.
Yeah, in this case, it would also be one, but now this is 1 second, right? Okay, so now we got a unit, right? So one, but so let's put this in seconds. So that could be 1 second, right? Okay. All right, now, okay, so I have to clean that table up a little bit more, but let me do another example. All right, how about this one? Okay. How many beats per second were you guys hearing?
I think
Kind of like two. And how many seconds between each beat?
0.5.
Yeah, 1/2 or 0.5. Right. Okay. So let's go back to the title here and add a little bit of info. Okay. So there's a physics name for the time between beats. It's called
Frequency.
time period. Yeah, time period. Right. Right. And I can use what variable to represent that? Yeah, capital T. Right. Now the flip side of that, which okay, the number of beats per second. What's that called in physics?
Frequency. Right?
Yeah, frequency. Frequency. Might just use the letter F for frequency. Okay. Guys, what's the unit for frequency?
There's capital F, right? Or
Well, okay, well the variable letter is F.
the look of line.
Hertz.
Yeah, hertz. That's what I'm looking for. Yeah, hertz. So Hz for hertz, like units, right? So time is measured in seconds. Frequency is measured in hertz. You guys get that, right? Okay. Let's do how about this? How many beats per second were you guys hearing?
Like 3.
Yeah, it's doubling, so great, about four, right? And if you're hearing 4 beats per second, how much time was there between beats? Yeah, a quarter or 0.25. Right. And then, so you guys see the pattern? I wonder where the next one's going to be. Okay. How many beats per second up?
8.
Yeah, goes to 8. So the time between beats is,
8.
1/8. Yeah, there you go. Okay. Right, so, okay, so there's a pattern here. Like if you know one of these columns, you can know what the other column is. And the pattern goes, frequency is what compared to time period?
Like or
1/the time period?
yeah.
Okay. Or vice versa, time period is 1/the frequency. Okay, so these guys are reciprocals to each other. Okay, so 1/8 is 1/8, and so on. Okay. Okay, so there's frequency and time period. Okay. Now, guys, if I kept increasing the number of beats per second, but you could count on when it was 8, but what if it was like 16, 32, 64? Okay. Do you think at some point your brain would not be able to distinguish the individual beats? It might sound more like a hum, like, and then if I kept increasing it, like an increasing pitch. Okay. Which brings me to, what if I had 440 of those beats every second? About 440 hertz. Okay. What does that represent? An A note. Yeah. A note. Like on a musical instrument. It could be that. Okay. All right, so hold on to this because I do want to come back and talk about music, but I gotta give you guys a recap of some concepts you saw last week, some labs you did, right? And then I'll probably come back to music and eventually look at author. Okay. So last week, beginning of the week, you guys did this pendulum lab. Right? I gave you guys some string and some mouses, right? And you were swinging them and timing these things. And I said, hey, let's change some variables and say how does that affect the time period. Okay. This was what we arrived at the conclusion of that lab. Okay. So let's run some. Let's say you have some string, you have this little lab right here. Let's swing back and forth and take some time period to swing back and forth. Okay. What if you take the length of the string and you double it? Okay, it's double the length of the string. What happens to the time period for double the length of the string?
Double, right? Or not double.
It increases, but it doesn't quite double though. Okay? As if I throw a factor of 2 on this L, go from L to 2L. Is this underneath the square root? The square root of 2. What is that? What is square root 2? It's like 1.414. Is that okay? So if I went from say 10 centimeters to 20 centimeters, double the length of the string, the time period increases by how much? 1.414. Oh, this. Oh, what if I take this pendulum? Here it is on Earth. On Earth. Swing, swing, swing. And I take this to the moon, which has a very weak gravity field. There's some gravity, but not very much. Okay. Is this going to swing? What happens to the time period?
It gets
It gets much bigger. I was like, right, it gets a lot bigger. Okay. So actually, if it's 1/6 of Earth gravity, let's see what that would be. What is the square root of 1/1/6? Okay. Maybe like about 2.5 times it would take. 2.5 times to swing back and forth compared to Earth. Let's see that. Okay. How about this? What if I replace this mouse ball with this big guy right here? Oh yeah, it's way heavy, way more massive, way heavier. Now what happens to the time period? Stays the same because mass is not part of this equation. It doesn't matter what the mass is. Right? Of course, you guys saw that last week. I'm just to remind you guys. Hey, what about this angle right here? Haven't mentioned this guy yet. But what if I had it at 5 degrees and it swings back and forth? It's like double that to 10 degrees. Now what happens to the time period? Also stays the same. Yeah, going from 5 to 10 degrees doesn't really change the time period. No. Okay. Later last week, you guys had this lab. Okay, you took some lab weights, hooked them to a vertical spring, pull it down, let it oscillate. It took some time to oscillate. First time out with a stopwatch. Guys, what if you double the mass? Go from, say, this mass to this mass. That could be double the mass, 100 grams to 200 grams. If you double the mass, what happens to the time period? It does increase by how much?
4.
Mm,
We're not half of them.
If I throw a 2 on that M, it's under the radical. Hey, is that what we did before? Is that the root 2? 1.4? Yeah, it takes 1.4 times the time to oscillate back and forth. Okay. What if I replace a very loose spring with a small spring constant? Here's a small spring constant, the green one. Okay, it's not very stiff at all. Okay. With a stiffer spring. Ooh, this one feels stiffer. Ooh. Okay. What if I take the same lab weight? Ooh, here's identical looking lab weights. Okay. I attach them to both these springs. A loose spring versus a stiff spring. Guys, how much time does it take to oscillate on the stiff spring compared to the loose spring? Less time or more time?
Less.
Yeah, less time. Yeah. If I pump up this K really, really, really big, those fractions getting smaller. Right? So here, just to animate it for you guys, here's the loose spring. Right, here's the stiff spring. You guys kind of see that? Yeah, that makes sense, I think. Something like that. What if I take this process? Here it is on Earth. Whoosh, whoosh, whoosh. That's on Earth. Let's take this to the moon with a very weak gravity field. What does this look like on the moon compared to Earth? The same. It's exactly the same. Gravity field is not part of this equation. Oh, got that. Okay. Oh, here's we did this earlier today. Right, time period frequency reciprocals. Okay. If you take that frequency, whatever it is, and you simply multiply by 2 pi, you get something called angular frequency. Then you can construct these type curves. Right, so height versus time. You guys made this curve as part of one of your labs last week. It bounced up and down. Right. Okay, so they can feed in there. Okay. A lab that I have planned up for you guys later this week is going to be this right here. So here's what possibly tomorrow. I'll give you guys some PVC pipes and beakers of water. And you can raise and lower the PVC pipe in the water. You see that? And the water's going to close one end automatically. It doesn't matter how long the pipe is. Okay. And then hold a tuning fork and strike the tuning fork. Bang! Okay. Now, there are certain places where it will resonate because it will create a standing wave. And this is exactly what it's going to sound like. Be really loud, right? If you take that distance and you approximately triple it, so if it is 10 centimeters, and you go to approximately 30 centimeters up here, okay, the same story. You create a standing wave. Now, we talked about different kinds of waves. Right, let's look at waves here. Right. So maybe here could be a wave. We got speed equals wavelength times frequency. Here's the wavelength, wavelengths. Okay. Frequency is one other time period. We got that. Right. There are these different categories of waves. So here's your classic transverse, which is easy to draw. Just whip off an S shape. Right. The one that's very difficult to draw is longitudinal. Right. Guys, what is sound? How are you hearing me right now? Because there's what kind of wave traveling through the air? Longitudinal. Yeah, it's all these high and low pressure points. High, low, high, low, high, low. You guys see these high and low pressure points, right? Okay, now we're going to take this longitudinal wave. We're going to put it down in this pipe. Now, guys, right above the water level, is that a high or a low pressure point? High pressure. You guys see all those molecules bunch up together? Okay, and then it could, go high, low, high, low. What do you guys think is at the opening of this pipe, high or low pressure?
Low.
This would be a low pressure. You guys see that? Right. Now, for whatever frequency is on this tuning fork, because it could be like a musical note. Okay. That the speed of sound is whatever it is. Okay. So we've locked in place a musical note frequency. We've locked in place the speed of sound. So there is some locked in place wavelength. Okay. Here I'm looking at a quarter of a wavelength. Here's 3/4 of a wavelength. Maybe these are longitudinal. It's common to whip off transverse looking waves to represent longitudinal, even though they're not really. Okay, that's a common thing. All right, so you get a lap paper looks like this fairly soon. Right. Ooh, what if I have a pipe that's open at both ends and some wind is blowing through? Right, instead of a standing wave. What do you guys think is right in the middle right there? Is that a high or a low pressure point? Yeah, high pressure and then low on the ends. Makes sense. Okay. Again, I drew them as transverse, but they're really longitudinal. Okay. Now this is truly transverse. Actually, I do have a demo for you guys on this. Let's get a look here. No, over here. All right, looks on string. All right, so there's this vibrator oscillator on the left side. All right, it's gonna bounce up and down. The string bounces up and down. Okay, so we got that. Okay, okay, 5 hertz doesn't look super exciting. Okay. But there are certain frequencies where you're going to see a standing wave develop. Right, so, right, not yet. Not yet. It's kind of muddy. It's not really doing anything interesting yet. Ooh, wait, something happening. Ah, there it is. Okay, so he's calling that 11 hertz, and then positive there, 11 hertz. Okay. Now if I go ahead a little bit, and he's going to keep increasing the frequency. Right. Ah, notice he doubled the frequency. Now, now we have it looks like that. Okay. Oh, guys, how about this? How many total wavelengths do you guys see right here? How about one? Do you guys see one full S shape? One full S shape is one wavelength. Now, if I go back to the 11 hertz situation, yeah, that is a half of a complete wavelength because it's only half the story. So that's half a wavelength. This is one wavelength. That's one wavelength. All right, how about? All right, it's kind of muddy. Ooh, there we go. 33 hertz. How many total wavelengths do you guys see right there? Yeah, 1.5. No, there's 1 and then a 0.5, 1.5. Okay. So I had a little bit more. No, it's just kind of. There's 44 hertz. No, so it looks like every 11 hertz, it's creating another standing wave. Right? How many total wavelengths do you guys see?
2.
Yeah, that's 2 complete wavelengths. 2. Okay, and then let's do another one. Wait, why did you go back to that? All right, okay, 66 hertz, 3 wavelengths. We got that. All right, so we got that. All right, so standing waves on strings. All right. Okay, so I'm getting closer to music here. Let's look at stringed musical instruments. Stringed instruments, for example, the guitar string could be a piano string, something like that. Right? You guys ever tuned a stringed instrument? Right? Turn the tuning peg. Right? You're directly changing the tension, but as a result, that's changing the musical frequency, like the musical note, right? Something like that. Right? Now, here's the big picture connection. Right? So, string instrument is going to vibrate like this. Okay, again, how many wavelengths total is this right here? Yeah, that's half a wavelength, which is right here. So, the length of the string represents lambda over two, or vice versa, like I drew here. So the full wavelength is actually double length of string, like on oscillation. Okay. Now here's your wave formula: speed equals wavelength times frequency. Remember last week I mentioned the example of like ocean waves. So if you're watching ocean waves come in and crash on the shore, if you could count the distance from crest to crest, that could be the wavelength. It's like 10 meters or whatever. Okay. And suppose the waves come in and crash every like 5 seconds. Because if it's 5 seconds between crashes on the beach, what's the frequency? Yeah, yeah, 1/5 or 0.2, and that'd be hertz. Okay. So you could figure out how fast those ocean waves are coming in. That could be the speed. And the water molecules themselves might just be basically bouncing up and down, but it's really an energy propagation is what it is. Right? Right, so anyway, back to the string instrument. Right. Here's the speed of a wave based on the tension in the string and the linear mass density, right? Mass per length. So that'll connect how tightly you turn the tuning peg, and the musical note is this out right here for frequency. Okay. Okay. All right. So got this. All right. Did I tell you guys about Pythagoras and the? No, I don't think I did. Okay, that's it. So back thousands of years ago, according to the story, Pythagoras was walking along the street one day. He hears these craftsmen like hammering these pots. They're making these pots going pow 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 hammering, right? And they're going like clang 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 clang, all different sounds. And he notices that some of these sound good together. Like, oh wait, that pot right there and that pot right there, come at the same time, like, right? Hey, sounds good. What do you think he sort of stumbled upon? Starts with an H.
Hertz?
What it's musical term. Harmony. Harmony. Yeah, harmony. You realize that some of these pots were sort of harmonizing. So, oh, that's interesting. So they started measuring the diameters of these pots and realized, hey, there are certain interesting ratios where they'll harmonize. Right? One ratio was 3 to 2. For example, maybe one pot was 20 centimeters wide and another was 30 centimeters wide. That's a 3 to 2 ratio. Those sounded really good together. Okay? And our modern terminology would say that's the fifth, or like the perfect fifth compared to some root note, something like that. So the certain ratio. Now I don't have all of them here. I only have just a few notes. Okay, but you can see a pattern here. So whatever your root note is, like, and you can assign some frequency to it. And we did for one earlier today. We were saying that one of the A notes, here it is right here, is 440 hertz. Okay, guys, what if you want to go up one octave? So you're still hitting an A note, but it's just one octave up. What do you guys think the A above it is? How many hertz? It says it right. Yeah, 880, because you just simply double it. If you double the frequency, you're going exactly one octave up. Okay? And what if you want to go one octave down? What do you think this would be?
Okay.
Yeah, 220 hertz. Yeah, and an octave below that would be 110. Yeah, yeah. So you guys see a pattern here. If you go double or half, you can hit the same note, just you're going up or down octaves, right? But what if you want to hit the notes in the middle? Right? Because if you lay out a piano roll, how many unique notes are there before you cycle back to the next octave? Like including all the white and black keys, all the keys.
12.
12. Yes, 12. Right, I'll show you guys. Oh, here you go. Right. Let's see. Hold on. Where's there it is. Yeah. All right. So here, start with the C note here. Okay. So if that's one note, this would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, when I say 13, that's a C, but an octave above. So it's really just 12 individual notes. Is that 12 notes, right? Okay. So that's Western music. A lot of Middle Eastern music, they'll even go to quarter notes. So how about 24 notes? But that's where we use it here. Okay. So, um, so how could you say like go to the fifth, right? The fifth, right? How many guys play a musical instrument? Who plays an instrument? Okay, about half the class. Right, pretty good. Right. So guys, if I say start at some root note, and let's say I'm going upward to get to the fifth, how many semitones do I have to count up? see, 1, 2, 3, 4, 5, 6, 7. It's like 7 semitones. 7, right? Or you could go down 5, either down 5 or up 7, right? Let's just stick to up 7 for now. Right. So from the C to this G, that could be like G is the fifth of C, like that. Right. So you go up 7 semitones. Right. Now, um, instruments a few hundred years ago used to be tuned differently than instruments are manufactured and tuned today. Right? Today they use a tuning uh, process called a equal temperament, right? Which is slightly different than these Pythagorean ratios. Like Pythagorean ratios are pretty good, these perfect harmonies and whatnot. Right? Uh, yeah, there's maybe sort of an advantage and disadvantage to the Pythagorean tuning. Right? The disadvantage is if you have one key established, whatever that key is, like key of A or key of C or something, right? It might sound like perfect, right? But as soon as you switch keys, like, oh, right, then the key you switch into is not going to be perfectly tuned anymore, right? Which is actually kind of interesting because what composers used to do, again, going back hundreds of years ago, is if they were going for like a certain kind of sound, like, oh, I want a song to sound like really happy or really melancholy or really this or really that, right? They knew they had like 12 different options to choose from, right? You know, kind of like a color palette. And say, oh, actually, this should be like E flat or something because that creates a special tone, right? Now, modern day instruments not like that. They use this equal temperament, right, which is going to follow this exponential curve. So if you're playing around within any key, the sort of disadvantage is within any key, it's not perfect, although it's really close. But then the advantage is you can switch keys and everything sort of sounds the same. Right? So there's no advantage of one key over another key. Right? And I want you guys to see how this lines up pretty closely to these ratios. So let's we were doing the example of the fifth. So where this n goes, let's put 7 for 7 semitones. Right? And remember, actually before that, let's do 12. Let's do an octave. Okay, so let's go up an octave. That'd be 12 semitones, wouldn't it? Guys, what's 12 over 12? 1. What's 2 to the power of 1? 2. Great. And whatever the root note is, say 440 hertz, if you multiply by 2, oh, look, you get 1 octave up. It's it. Great. All right, now let's try the fifth, which is like 7 semitones. So in your calculator, do this. Do, uh, we'll just do 2 to the power whatever. So do 2 to the power of, and then parentheses, let's go 7 over 12. 7 over 12. All right. So equal temperament. Right. And now, if this were perfect, if it aligned exactly with Pythagorean tuning, it should be what ratio for the fifth? Yeah, 3 over 2, which should be like 1.5 on the calculator, right, as a decimal. So if it were exactly perfect, it'd be 1.5. Let's see how close it is. Ooh, not too bad. 1.498. That's really close, isn't it? Right? And some of these notes are closer than others to the Pythagorean alignment. So, right, you guys good? Know that? Music going on? All right. Let's do a little bit of Doppler here. Okay, you guys ever stood up by the side of the road, car goes by? Yeah. Hear that pitch shift? Okay. But wait a minute. If you're inside the car, you don't hear a pitch shift. You just hear anything. Okay. But outside the car, hear a pitch shift. Huh. What's that about?
You're like a bird, you're looking right down in the water, and there's a bug sitting there. And this is a lake that's perfectly smooth. But now what the bug starts to do is the bug starts to jiggle up and down. And when that bug jiggles up and down, that bug is a vibration, yeah? Right. And that's vibrating on a nice surface, yeah? We're going to make what? Begin with a W. Ripples. All right, all right. We're going to make waves, gang. We're going to make waves, okay? And the waves kind of look like this. Where I draw the line, that represents like the crest of a wave, like it might sort of be like this. Can I see what I'm saying? Okay, so this represents the crest of the waves. And the waves go out in all directions. And the fact that they're circled,
let me get this. All right, back here.
Is kind of evidence that they go out in all directions at the same speed. Isn't that true? Right. Like if it went faster over here, then the wave would sort of be like that, yeah? Okay. So the circles are evidence of the same speed. Okay. Now, what would be the frequency of the waves compared to the frequency of the vibrating bug? In other words, if you put your hand here, blip, 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 the waves would hit your hand, yeah? Certain frequency. How would that blip, 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 compared to the whoop, whoop, whoop of the bug? Same. Isn't that right? The frequency of a wave is the same as the frequency of the vibrating source. Makes sense, doesn't it? Let's suppose now that the bug swims in this direction. What the bug is going to do is the bug is going to swim in the direction of the waves that it's producing, and it continues to vibrate a little bit, yeah? Wouldn't the wave pattern look something like this? Can you kind of be seeing that? In fact, what direction would the bugs be swimming, gang? I mean, you can tell it's going that way, right? Well, the bug might be at rest and the water's going this way. I mean, motion is relative anyway, yeah? Okay, now if I put my hand over here, would I get a higher speed wave, a lower speed wave, or the same speed wave? Check your neighbor. And make sure you're listening to the question that's being asked. How many people say, hey, the speed of the wave is going to be the same? Yeah, that's right. The speed of the wave doesn't change. What does change, gang? How frequently that wave encounters you is different, yeah? So I can get a different frequency. When I put my hand here, higher frequency or lower? Can you see it? Over here. Bloop, bloop, bloop. That change in frequency due to motion of the source or the receiver is what we call the, named after a person. Okay, good. It is called it's a Doppler effect. That's right. The Doppler effect is the change of frequency when something moves toward you, away from you, that sort of thing. The change of frequency due to motion.
All right, sticking that a little bit deeper here. Right, so this could be the bug in the water, or hey, now I got a car in the air. It's the same principle here. Right? And so here's you. You could be the observer, right? Observer. So OBS could be observer, right? And oh, source. Maybe this guy's maybe his engine's rumbling, or maybe he's beeping his horn. Beep beep. Either way, whatever story you want to attach it. What does it sound like inside the car? Probably just whatever would be at rest because you're at rest relative to the car. Right? What is this observer here when the car is traveling towards the observer? Right? So there's this whole Doppler equation. And what you need the speed of sound, which I'll give to you. It's approximately 340 meters per second, although that depends on the temperature and maybe the pressure. Okay? I got plus or minus speed of the observer right here, and plus or minus speed of the source, or maybe I should say velocity, because it also matters what direction they're going. Okay? Let's see if you guys can navigate the plus or minus. I have a whole worksheet on these that I'll probably give you guys later this week. Okay? So let's see if you guys can figure this out now, and then later on, if I throw some numbers at you guys. Okay? So suppose this observer is just standing here. He's not moving at all. Because if the observer is not moving, what is the velocity of the observer? 0. Right? Let's say the car is driving toward the observer. Guys, if the car is traveling toward the observer, does the observer hear a high pitch or a low pitch relatively? High pitch. You guys see that there's a very short wavelength? Okay. And the speed of sound doesn't change. The speed of sound, guys, are these all circles? These are all circles, aren't they? Like once the sound is released into the atmosphere, it just goes with the speed of sound. The speed of sound doesn't change. It's not the speed that changes. It's the frequency, right? The observed frequency, right? Yeah. So I got a very short wavelength here. So he's going to perceive that as a high pitch, right? And what I'm trying to lead up towards is, what should I do with this plus or minus? Again, the car's headed towards the observer. Should you add or subtract down here? Huh. Show of hands. How many guys think? Here, let me say the scenario one more time. Right. The car's headed towards this observer. Therefore, this observer here's a very high pitch. If the car's going beep beep, this guy hears beep beep. Here's a higher pitch. The way you get that, show of hands. How many say you should add down here? Who says you should subtract? Yeah, I'm going to go with subtract. Right? Because, guys, if you subtract, this denominator becomes smaller, doesn't it? Right? And when you put a smaller number in the denominator in an overall fraction, that makes the overall fraction what? Larger, which is say that whatever the source frequency is, suppose the source frequency is like 200 hertz, you're going to multiply by something more than 1, and that the observed frequency would be more than 200 hertz. That's a higher pitch. Right? And then vice versa. Is what if I put the observer on the back side of the car and the car's driving away? Meow. Shouldn't the observer now hear a low pitch? And how do you get that in the equation down here? You do a what? Like a plus. Ah, yeah, no, it'd be the opposite, wouldn't it? Okay. Hold this. Let's switch it. What if the car is stationary and then the observer is running back and forth? If the observer is running towards the car, should you do plus or minus on top? Observer's running towards the car. Does he hear a higher pitch than if he was just standing still? Yeah, a higher pitch. How do you get a higher pitch on top? Probably add. Guess the add, right? What if he's running away from the car, running away? Yeah, subtract on top. Okay, right. So you guys can kind of navigate this, right? And probably throw some numbers at you guys in the near future. Right? Hey, guys, could this car be going so fast that it's actually outpacing the very sound waves it's sending out? Is that possible? It's not called supersonic, faster than sound, faster than sound, right? Right, get something like that. Right. Actually, if you're going faster than sound, suppose you're like 3 times the speed of sound. That's called Mach what? Mach 3. Ah, about 3 times the speed of sound. Okay. And guys, look what basic shape that makes. Think in 3 dimensions. And 3 dimensionally, what shape would this be? A cone. A cone. Right. I suppose my pen top right here is an observer. Has the observer even heard the jet yet? The jet's already passed him. He said, "Hey, I watched that jet just go over past the supersonic jet. Just passed me. He hasn't even heard it yet. Has he heard it now?" Yeah. In fact, when this cone wave passes, this observer experiences a what? Sonic boom. Sonic boom. Yeah. And I gotta. There we go. Let's check this out. Got some videos, some sonic booms here, well, some cone waves. Let's watch these supersonic jets. Watch this here. Ah, you guys saw that cone shape? Maybe rewind a little bit. Cone shape. Ooh, we got a bunch of these. Yeah, there's a little flat cone there. Hey, guys, if it's a flat cone, it's probably just going a little faster than the speed of sound. And then the narrower the cone, it's going significantly faster than sound. Yeah, see that right there. All right, I'm gonna.
What if there's a circle around them?
If it, huh?
Like, I saw a rocket launch, and then
Okay.
there was like a circle around the rocket, and then it.
Ah. Okay, probably like near the end here. I think there's a similar. Right, let's see. Oh, something like that.
No, like just around like the top of it. I have a picture on my phone if I.
Huh. Maybe you have to show me later. Yeah. If you're standing like beneath it, maybe it looks kind of. See that, right? But anyway, I do want to fit in this Kahoot though. I think we have just enough time. So where's? Here we go. All right, you guys got your laptop ready to go? Classic mode. Let's get this going. All right, so here's a Kahoot on Waves.
And inside information for pilots. Then Glenn Pugh.
All right, we're back. Pins on the board if you're still about to hop in. Yeah. Let's see what you guys know about waves. All right, we got about 14 minutes to do 20 questions, so this might be a little fast paced, but that's all right. The time needed for a wave to make one complete cycle is called its time needed. Yeah, time period, or just period if you like, right? That's the amount of time, right? Now, the distance it travels in that time period is called the wavelength, so that kind of matches to it, but it's a different concept, right? So this one's time, this one's a length, right? And then the reciprocal time is the frequency. Right? So got some related ideas there. Right? All right, got Nick, Anna, and Weird Fishes getting some points. Sound is an example of what do we call that? Yeah, longitudinal or a pressure wave. Yeah, it's a pressure wave. Needs a medium to travel through. Longitudinal pressure wave. All right. Golden JE, Triple X, Injection, Geon, Anna, Weird Fishes. When two or more waves, same place, same time, the resulting effect. Ooh, this goes back to last week. Yeah, you guys remember constructive and destructive interference? You guys remember that? Interference patterns? Let's see. If I gotta. Here's one of them. You guys remember this from last week? All right, let's watch this play out. There's some destructive interference. All right, back to here. All right, we got Tinjaction, Golden JE, Anna, Gion, weird fishes on fire. Where can you touch a standing wave on a rope without disturbing the wave? Ooh, kind of a picture. Yeah, at a node, right? One of those nodes that doesn't actually really move on a standing wave. Right? Standing waves can be set up. Yeah, all the above, right? Now, this one's going to be a lab coming up soon with PVC pipe and water. Organ pipes is fairly similar. Stringed instruments are more like transverse, but yeah, they could all be standing, right? If they're like resonating in place. Got nodes and antinodes. All right, Golden JE, Tinjaction, Gion, Anna, weird fishes. Bug is jiggling up and down and swimming towards you at the same time. Compared to the frequency that the bug is emitting waves, the frequency of the waves reaching you, maybe this guy right here, is a what frequency? Yeah, it'd have to be a higher frequency. You would perceive a higher pitch, like a higher musical note, right? And then when you do the math, make sure the math would be consistent with that. You got Nick Broker, Injection, Gion, Anna, weird fishes. Jiggling up and down, swimming towards you at the same time, compared to the speed at which the bug is emitting waves, the speed of the waves reaching you. What happens to the speed of sound? Once that sound is released into the atmosphere, is it just going at whatever the speed of sound is? Yeah, it didn't really care about the source anymore at that point. It's just, yeah, look at you guys. Yeah, that's right. That's right. Yeah. The sound of a car's horn passes proceeds away from you. The pitch seems to. Yeah, decrease. Right when the car's going away from you. Right. All right. The Golden JE, Injection, Gion, Anna, weird fishes. Doppler effect is the change in observed frequency due to motion of the source or the observer. Right. The equation I've just shown you guys a few minutes ago can handle motion of either or both. All right. So there has to be relative motion to observe a frequency difference. You double the frequency of a vibrating object. What happens to the time period? Yeah, half. Remember reciprocal? That was the first demo at the beginning of class today. You're hearing those beats going. You double the frequency, there's half the time between beats. Yeah. During a single time period, the distance traveled by a wave is one. One wavelength. So one wavelength in one time period, they correspond. That one's a distance, one time. Golden JE, Tinjaction, weird fishes, Gion, Anna. Child swings back and forth on a swing. What if he stands rather than sits? Now, because what that would effectively do to a pendulum is it would make the pendulum shorter. So another way of saying this is, if you make a pendulum shorter, what happens to the time to swing back and forth? It's the same question.
The time period. Oh.
If the pendulum is shorter,
Oh wait, no.
right. If it's a long pendulum, it's like swing, swing. If it's a short pendulum, it's like swing. Yeah. So the time period is going to decrease. Right. Golden JE, Tinjaction, weird fishes, Anna, Gion. Suppose a simple pendulum suspended in an elevator. When the elevator accelerates upward, does it feel like somebody just turned up the gravity? Ooh, now we feel really heavy in there. Somebody just turned up the gravity. What happens to the time period?
Yeah.
Well, I know in deep space it wouldn't swing at all.
I knew it.
So that'd be like infinite time period. Maybe on the moon it'd be a large time period. On Earth, it gets smaller. In a heavy gravity field, it'd be really tiny time period. Just swing back and forth really fast. Yeah. And which is what it would feel like in an elevator. Yeah, it's like somebody just turned up the gravity. All right. Golden Jade, Injection, Weird Fishes, Anna, Gion. Observer on the ground hears a sonic boom created by an airplane flying at. Yeah, greater than the speed of sound. It's called supersonic. Faster than sound, supersonic. Oh yeah. Sound waves that has a higher frequency has a wavelength. These are all the same speed. They're all the speed of sound. Higher the frequency, the shorter the wavelength. That's speed equals wavelength times frequency. You can back that up with. Okay. Golden JH, Injection, Weird Fishes, Anna, Gion. Two waves, same place, same time, exactly in step with each other. Each has an amplitude of 1 meter. What's the resulting wave amplitude? Sounds like constructive interference, doesn't it? They're in phase, same place, same time. 1 plus 1 is 2. 1 plus 1 is 2. You guys got that? Okay. We got, here's my, let's see, watch this real fast. Here's constructive interference. Whoosh. There it is. 1 plus 1 is 2. Oh, yeah. Oh, yeah. Got Golden Jade, Injection, Anna, Weird Fishes, Gion. Wait at the end of a spring bobs up and down. Boing, boing, boing. 1 cycle every 2 seconds. Every 2 seconds. That means its time period is. Wow. Wow. 2 seconds. Yeah. All right. Could you say its frequency is half a hertz, but its time period is 2 seconds? Every 2 seconds it cycles. All right. Leaf on a pond bobs up and down 2 cycles every second. What's the frequency? Boom, 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 boom. 2 cycles every second. That's a frequency of 2 hertz. Right. Now the time period between bobs would be half a second, but the frequency is 2 hertz. Right. 2 cycles per second, 2 hertz. Golden Jade, Injection, Weird Fishes, Anna, Gion. Wave travels 10 meters in 2 seconds. What's the wave velocity? 10 meters, 2 seconds. Sounds like 5 meters per second. There you go. I've got Golden Jade, Injection, Anna, Weird Fishes, Gion. We're going for the win. You guys ready for the win? For the win. Here, I think I have to walk you guys through this one a little bit here. Wave has 2 crests and 2 troughs each second. Does that sound like a frequency of 2 hertz? Here's your wave formula. Frequency. We know that frequency is 2 hertz. Everybody knows that? 2 hertz. Okay. If the wave travels 120 meters in 3 seconds, oh, guys, 120 meters in 3 seconds, what's the wave speed? 40 meters per second. So where the speed goes, let's put 40 meters per second. Right? What's the wavelength? So here's what we got. 40 equals lambda times 2. You guys got that? 40 equals lambda times 2. So what's the wavelength? Yeah, 20 meters. 20 meters. All right, let's see who won Kahoot. With the bronze, Anna. Silver, Weird Fishes. And gold, Gion.